Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd Scribblecast, where you can download organic chemistry lectures and solution to homework problems. In today's lecture, we're going to take a look at resonance. In order to introduce the concept of resonance, we want to begin by drawing a Lewis structure for the molecule CO3 2-, and take a close look at the structure of the carbonate dianion. Now, in order to do the Lewis structure of carbonate, we need to calculate the total number of valence electrons. And the total number of valence electrons and that equals 4 for carbon. Oxygen has 6, and there's 3 oxygens, so 3 times 6, plus 2 electrons for the negative charge. That gives us 18, 20, 24 electrons. So now we can draw our carbon, give it its 4 electrons. We can add our oxygens, which have 6. We can add an oxygen, which has 6. We can add an oxygen, which has 6. Now, what we're going to do is we've got to remember that we added 2 electrons for the 2- charge. I'm going to put them on oxygen because oxygen is more electronegative, and I'm going to give 1 to each oxygen. Now I can start sharing electrons to make sure I get 8 electrons around every atom. And if I look at these 2 oxygens now, I've got 2, 4, 6, 8. 2, 4, 6, 8. Those 2 oxygens are happy. Carbon only has 2, 4, 6, so we can share some electrons here. And if I look at what I've done, I've got a carbon, single bond to an oxygen, which has 3 lone pairs, single bond to an oxygen, which has 3 lone pairs, and the oxygen over here has a double bond. Now there are several things I can do with this Lewis structure. I could, for example, determine the formal charge of each non-hydrogen atom to determine where the charges are. I can also determine a hybrid orbital number for the central carbon and determine what the hybridization of the carbons and the oxygens are. We're going to actually begin by doing formal charge, and I am going to label the 2 different types of oxygens that we have. And the 2 oxygens we have are oxygen alpha, which is the oxygen. Oxygen alpha is the oxygen which has the double bond. And I'm going to label oxygen beta, the 2 oxygens with the single bonds. And they're both beta because they're both the same. And so I'm going to now begin a formal charge calculation. I'm going to start with carbon, a formal charge of carbon, formal charge of my carbon atom. Carbon has 4 valence electrons from the periodic table. And if I count up the number of electrons it has around it in the structure from equal sharing, assuming equal sharing, carbon gets 1 electron for each bond. 1, 2, 3, 4. Has no lone pairs, so 4 minus 4 equals 0. Formal charge of oxygen alpha equals, oxygen has 6 valence electrons from the periodic table. When I get to the oxygen with the double bond, oxygen alpha, the lone pairs are counted totally for oxygen because they're not shared in a bond. The double bond, each bond component in the double bond donates 1 electron to oxygen, so that's 2, 4, 5, 6. 6 minus 6 equals 0. So the oxygen with the double bond has no charge. Now the formal charge of oxygen beta. Again, we have 6 valence electrons, and we need to subtract how many electrons around each atom. Oxygen beta has 2, 4, 6 electrons in lone pairs and gets 1 electron from its bond for a total of 7. 6 minus 7 equals -1. Now there's 2 of them, of course. So 2 times this 2 oxygen betas gives us a -2 charge. So if I add this up and check my net charge, that net charge equals -2. And you see that matches the formal charge. Also, I should check to confirm I have 24 electrons. If I count my electrons, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. So the net charge confirmed, the valence electrons confirmed. This structure works. I can check the hybrid orbital number of carbon, the H.O.N of carbon. Remember, hybrid orbital number is the sum of the atoms and lone pairs. Carbon has 3 atoms and 0 lone pairs, which equals 3. Now, hybrid orbital number gives you an sp² structure. So now I can draw it with the correct shape, and I'll do that. And so I'm going to just rub out my valence bond equation, or at least this part of it. I'll move the 24 up, if you like. Give me some more room. So the valence bond electron count was 24 electrons. Okay, so here is my structure for the carbonate anion, and we know there's a -1 charge on this oxygen and a -1 charge on this oxygen. Now, what's interesting about this from an experimental viewpoint is the fact that the structure we draw with the valence bond structure, the Lewis structure, has a problem when compared to what is known from the actual X-ray crystal structure determination for the carbonate dianion. Now, looking at the Lewis structure, we know that single bonds are longer than double bonds. And so we would predict that carbonate dianion should have two long bonds, 2 long carbon-oxygen bonds, and 1 short carbon-oxygen bond unit caused by the double bond. The X-ray crystal structure determination reveals that all the carbon-oxygen bond lengths are equal. The reason for this is that this structure does not exist. In fact, you can get a clue as to what's going on if one asks the question, why did you draw the double bond to this oxygen? Why, for example, couldn't you draw it through the oxygen that is up? Why couldn't you draw it to that oxygen? Then you'd have something like this. Or why couldn't you have drawn the double bond to the oxygen on the left-hand side? Well, in actual fact, I guess we could have. They are the same structures in the sense that I could rotate the atoms. But what's interesting about these structures is that one could argue that, well, maybe if each different oxygen position could theoretically have the double bond, maybe they all share it in some way. Share that double bond. In actual fact, this concept is similar to the truth. Now, we're going to draw this again, And we're going to introduce the concept of resonance with this structure. Okay, so let's draw all three structures again across the top. And what we're going to do is draw what is called the resonance structure. They're also called canonical structures or contributing structures. And so we're going to draw what we just had. Trigonal planar, because it's S, the carbon is sp squared. So here's my original structure. I'm going to draw it again over here. And this time I'm going to put the double bond straight up. And then I'm going to draw one more. And this time I'm going to put the double bond off to the left. Okay, so essentially all I've done is shift the double bond. Now what's interesting is the resonance structure is a structure, or the canonical form is the combination, or is any individual structure that we've drawn here. But it is not the true form. The resonance structure represents one of the closest structures that is a true Lewis structure that can be infer the structure of the true form. What is the true structure? Well, the true structure is called the resonance hybrid. The resonance hybrid. Now, the resonance hybrid, we said, had oxygen bonds that were all equal length. In fact, the oxygen bond length was somewhere in between that of a double bond and single bond. Okay? It was 33% shorter than a single bond, which suggested there's some double bond character. So I could represent this with some kind of dotted dash. Now, when we did the Lewis structure, we found out that single bond oxygens had the negative charges. But what's interesting is if we share the double bonds like this, each atom ends up with a 2/3 negative charge. In our resonance hybrid. Now, the resonance hybrid is what really exists, but how do you draw something like this for a Lewis structure? You can't, because one of the fundamental premise of valence bond theory is that bonds exist between two atoms. And what these dotted lines suggest is that we've somehow smeared out the pi bond of the double bond over all these atoms. And so valence bond theory can't handle this. So how do we represent this in the case of a Lewis structure? Well, the best Lewis structure that we can come up with to do this is the resonance structure. So these structures, these three structures, each one of them is referred to as a resonance structure. They're also called canonical structures or contributing structures. What's interesting is canonical structures, contributing structures, resonance structures, they're all the same thing, don't exist. When they are all superimposed on each other, they give you the closest representation that a Lewis structure or valence bond theory can give that might represent the resonance hybrid. Now we connect these resonance structures by a double-headed arrow. They are not in equilibrium. These structures don't exist in solution. So we don't use equilibrium arrows, we use resonance arrows. A double-headed arrow like this means resonance. And these structures don't have any existence, physical existence in reality. If you like, the resonance arrows mean that if you take these three structures and you merge them, by averaging them all together, you'd get a close representation of what the resonance hybrid is. Now, the resonance hybrid is more stable than any single resonance structure by what we might call the resonance energy. The resonance energy is that energy which the resonance hybrid is more stable than the most stable of the resonance structures. And in this case, all three resonance structures are identical. That is, two single bonds oxygen and a double bond oxygen. So they all make equal contribution to the resonance hybrid. They all make 1/3 contribution. The resonance hybrid forms because it gets the molecule to lower energy. It spreads the negative charge out by taking those pi electrons of the double bond and smearing them out over many atoms. And valence bond theory has a very difficult time handling that. And so the way around that was the theory of resonance. Now, we have some rules that we can exercise on how we carry out this type of resonance, or write these structures. And those rules, when applied, give us a lot of information and allow us to also to determine which structures are the major contributors. As I said, in this case, since the structures are so similar, they all make equal contribution. But that's not always the case. So let's start with some rules for writing resonance structures. So rules for writing some resonance structures. And the first rule that you must always remember when you're drawing a resonance structure is that resonance structures involve a change in the position of electrons only. We do not rearrange the atoms. The atoms, for example, the carbonate, the carbon was in the middle, the oxygens were around it. We only move the electrons. Point 2, what electrons can move? Well, only the lone pairs. We only move lone pairs. Only lone pairs, which are the non-bonding electrons. And pi electrons. Pi electrons are those in the multiple bond. So only lone pairs and pi electrons, or pairs of electrons in the pi bond, can move. Okay. Sigma bonds never shift. Now, Rule 3 is interesting because it's a slight variation from our Lewis structure rules. In Lewis structure rules, we stated to be a proper Lewis structure, you must have always 8 electrons around every atom other than hydrogen. Hydrogen could only have 2 electrons. But every atom tries to get to 8 electrons. And there were only 2 exceptions to that for Lewis structure. The first was boron and aluminum, which can have 6. And the second were third row elements. Okay, but in the second row elements, they had to have 8 electrons around them, or it's an improper Lewis structure. In resonance structure, period 2 elements must have no more than 8 electrons. We can draw resonance structures with only 6 electrons around them. They're not proper Lewis structures, I agree. But they are acceptable resonance structures, albeit minor ones, but they are acceptable. So, period 2 are period 2 elements never have more than 8 valence electrons. Emphasis on the more. They can have less, but they can't have more. Never have more. Okay, so the first 3 lay down some rules on how we move electrons, what electrons we can move, how many electrons around the atom, etc. Now the next couple rules apply towards finding which resonance structure the hybrid is most like. The terminology we use for this is which resonance structure actually makes the greatest contribution to the resonance hybrid. And so if we look at this, Rule 4 states that structures, okay, resonance structures begin with resonance structures with filled octets resonance structures with filled octets are more important. More important means make greater contribution to the resonance hybrid. Are more important. Than those without filled octets. So if you have 8 electrons, that's better than having less than 8 electrons. Let's look at an example. I'm going to draw a structure here. It's actually a molecule called an aldehyde. When an aldehyde is placed in acid, a source of H+, the proton on the acid protonates a lone pair. And so it protonates the oxygen and you have a positive charge. I can draw a resonance structure for this, in which I've moved this pi electron out to the oxygen. So I'm only moving the pi electron. I'll show you with an arrow. Move those pi electrons out to an oxygen, and I create a lone pair here. So the pi bond is moved out to the oxygen, so I'm left with a single bond to oxygen. And I get two lone pairs now on the oxygen. And if I do formal charge, like, how do I know the plus was on the oxygen? The plus was on the oxygen. I did formal charge in my head here. Okay, oxygen has 6 valence electrons, and I subtract from it half the bonding and the lone pair. 2, 3, 4, 5. 6 minus 5 is plus 1. Now, where is the positive charge? Well, oxygen now has 6 minus 2, 4, 5, 6. 6 minus 6 is 0. Carbon has 4 valence electrons. There are 3 bonds, so carbon gets 1, 2, 3. 4 minus 3 is plus 1. Plus is now here. This is a resonance contributor. Neither of these structures represent the true structure, which is the resonance hybrid, so neither exists. But which one is a closer representation of the resonance hybrid? We can determine that using Rule 4. Count the electrons around the atom in the first structure. Well, hydrogen has 2. They should. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Now we're counting all the electrons because we're not doing a formal charge calculation. Let's go over here. Oxygen, 2, 4, 6, 8. This carbon, 2, 4, 6. The right-hand structure, or what I'm going to call structure A has 8 electrons around every period 2 atom. But structure B, carbon only has 6 electrons. Because it has only 6 electrons, it is not its favorable structure. It's an extremely minor structure. So A is greater than B in its contribution to resonance hybrid. That simply means that the resonance hybrid, the true structure, looks more like A than it does B. Now, these rules for determining contribution are prioritized according to number. That is, this first rule that I've given you is the paramount rule that you always check first. But sometimes you can draw resonance structures where there is no difference in filled octets. In that case, we need a new rule. And this is called the fifth rule. And it's broken into 2 parts, A and B. But the fifth rule, A and B, are only used when Rule 4 doesn't apply. If there's a tie in Rule 4, so you have to break that tie. Let's look at a situation where we have to apply another rule. For rules for writing resonance structures, I'm now going to begin with rule number 5. And this one's called A. What is 5A? The more important structures involve, the more important structures involve less charge separation. Now, this rule is only applied if the fourth rule is not violated. That is, all the atoms have filled octets. Let's look at a structure that can exemplify this. Okay, so what we're going to do is we're going to take a look at a carboxylic acid called formic acid. And if I draw a carboxylic acid, looks like this. I actually can draw this structure slightly differently. And I'm going to show you through arrows that I can take a lone pair and make a pi bond sometimes. So if I take that lone pair and dump it in to make a pi bond, now we've created a problem if we do that. You'd get 2, 4, 6, 8, 10 electrons around carbon. So I'll move this pi out and create a lone pair. So you'll see I'll do this in my next structure. So now I've taken a lone pair and made a double bond here. And the double bond going up, I broke the pi bond of it and turned the pi bond into a lone pair, giving that oxygen 1 extra lone pair. So I have these two resonance structures. Okay, these two resonance structures, I can check the formal charge on the oxygens and carbons. If I check structure A, I'm going to label it A. Oxygen has 6 valence electrons. It has 2 lone pairs, so that's 2, 4. Take 1 electron from each bond, 5, 6. 6 minus 6 is 0. This oxygen has 0 charge. 6 minus 2 lone pairs is 4. 5, 6. 6 minus 6, this oxygen has 0. And finally, the carbon's charge, 4 valence electrons minus 1 bond, 2 bond, 3 bonds, 4 bonds. He gets 1 electron for each bond. 4 minus 4 is 0. There's no charges on this system. Notice that each atom has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. What about the other structure? Well, if I was to apply Rule 4 and check if it's got filled octets, 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. They all have filled octets. So Rule 4 doesn't help us. A and B are tied with regards to the filled octet rule. But let's do formal charge. On the oxygen here, the left-hand oxygen, I have 6 valence electrons minus 1 lone pair, that's 2. 1 bond, that's 3. Another bond, 4. Another bond, 5. 6 minus 5 is minus 1. The carbon has 4 valence electrons. Minus 1, 2, 3, 4 is 0. This oxygen has, a little careless mistake there. We'll come back to that. This oxygen, I'll tell you how I spotted I made a careless error, because this is useful. If you actually make an error like this, you can double check it. This oxygen has 6 valence electrons from a periodic table. 2, 4, 6, 7. 6 minus 7 is minus 1. Now, if I add up the charges, minus 1 and minus 1 is minus 2 plus 0. So that's minus 2. But this molecule, when I drew it, had no charge. Okay, I know this molecule was originally neutral. It still has to be neutral, so I've done something wrong. Let's go back to this first oxygen. Formal charge of oxygen, as I said, was 6. This guy has 1, 2, 3, and the lone pair 5. 6 minus 5 is plus 1. Now when I check the total charge, plus 1 minus 1 and 0, its net charge is 0. I haven't changed the charge. In resonance structures, the total charge must remain the same. Now notice what our rule states. It says the more important structure involves less charge separation. The reason for this is it takes energy to separate charge because charge is attracted to each other. Plus attracts minus. The right-hand A structure has no charge, but the left-hand structure, A, the A structure, has no charges on any atoms. Structure B on the right has a plus or minus charge that is separated. This separation takes energy, making B a less of a contributor. The actual resonance contributor, the actual resonance contributor A, is that structure that is most like the resonance hybrid. So A makes the greatest contribution, is greater than B. Now, the next rule, we call 5B, we look at if A doesn't work. And this is when you have the same amount of charge separation, you have 8 electrons around every atom. The more important structure is the one where the most electronegative atom has the negative charge. So the most important is the one where the most electronegative, that's a big word, let's write it, don't know if I can fit it on here, negative, I might have to hyphenate it, electronegative, all one word, where the most electronegative atom, most electronegative atom has a negative charge. Okay. And the molecule diazomethane gives us a nice example of this. Diazomethane is a very reactive molecule, good at generating CH2 units. And if I draw it in this structure, CH2N2, we have a structure that has 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around nitrogen, 2, 4, 6, 8 around the other nitrogen. Now I can draw a resonance structure where I dump one of these lone pairs and create a triple bond. If I do that, that creates 10 electrons around this nitrogen, so we're going to shift this pi bond to a lone pair on carbon. If we do that, we get a molecule that looks like this. Triple bond to nitrogen. We got the lone pair on carbon and a lone pair on nitrogen. And I'll put a resonance structure there. Now we can calculate, let's check, how about the electrons? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6. 2, 4, 6, 8. So every atom has 8 electrons around it. Now carbon can have its formal charge calculated. Carbon has 4 valence electrons. 4 minus 1, 2, 3, 4. 4 minus 4 is 0. Nitrogen has 5 valence electrons. 5 minus 1, 2, 3, 4 for half the bonding. 5 minus 4 is plus 1. This nitrogen, 5 valence electrons from the periodic table. 2, 4, 5, 6. 5 minus 6 is minus 1. Now let's do it for the next structure. Carbon, as I said, had 4 valence electrons. 1, 2, 3 for the single bonds. Lone pairs 2, that's 5. Did I say carbon has 5? I hope it has. I said it has 4 valence electrons. Carbon has 4 valence electrons from the periodic table minus the 5 electrons I counted. 4 minus 5 gives it minus 1. Nitrogen has 5 valence electrons minus 1 electron for each bond. 5 minus 4 is plus 1. Nitrogen has 5 electrons, minus 2, 3, 4, 5. This one is 0. So rule number 4 could not be used because all of the atoms of both structures have 8 electrons. Now let's try rule 5a. Rule 5a says the one that involves less charge separation. Well, what's the charge separation? You have a plus and a minus 1 beside each other. But you have that in both structures. So 5a doesn't help you. When 5a doesn't apply, we then try rule 5b. And we see for rule 5b that we have to find the more electronegative atom, bears the negative charge. Well, who's more electronegative, nitrogen or carbon? Nitrogen is. So the structure, and I'll call this one C, the structure on the left, which has the negative charge on nitrogen, makes a greater contribution to the resonance hybrid than structure D. C is greater than D for contribution. And because of that, the resonance hybrid looks or behaves is most like structure C. Now, we have some other points to make that are important after B, and they are labeled D and C, 5D and C. 5D, it's hard to come up with an example of this, so you just have to remember that having identical charges beside each other is extremely repulsive and unfavorable. It's very difficult to do. To get a structure, and I'm going to just use A, B, C, and D. If we did a formal charge in A, B, C, and D, and we found there was a minus on A, a plus on B, so there's some charge separation, and a plus on C and a minus on D, the adjacent plus produces a repulsive force. that is significant and destabilizes this structure. Adjacent positive charges leads to an unfavorable resonance contributor. Okay? And that should have been labeled C. Sorry. Now point D. So adjacent positive charges are unstable and unfavorable. So they lead to minor contributors. In point D, if you have charge separation, the closer the charges, the better. So adjacent charges of opposite sign are more favorable than when separated. A nice example, I'll use ABCD again. If you had 4 atoms bonded together, A, B, C, D, and you were able to get a plus minus on B and C, and then you drew a resonance structure, and when you were done, the plus and the minus shifted away from each other, so the plus was now on A, and the minus was on D. If all the other rules held true, then this structure would be the greater contributor, because this structure, the one I just circled, has the opposite signs closer together, and we know opposites attract. Now, when drawing resonance structures, you have to make sure, always have to make sure, that you don't unpair the electrons. Remember when we looked at dioxygen? We said the Lewis structure for O2 was not correct. We had to do a molecular orbital diagram, and O2 was found to be a diradical. And if you split the pi bond, you could put a lone electron and one oxygen alone on the other. Keep your 2 lone pairs. This would be a structure closer to what the molecular orbital diagram represents. Could I have split the electrons, that is, used a half-headed arrow, move one electron to one atom and the other electron to the other? Would these be resonance structures? And the answer is no. To be a resonance structure, if all the electrons are paired up to start with, they must still be paired up afterwards. And so we could not call these two things resonance structures. Okay. Always remember, in summary, point 7, contributing structures, canonical structures, resonance structures have no physical reality. There is not an equilibrium of structures in solution. It's the only way valence bond theory can draw them, even though they don't exist. No physical reality. Only the resonance hybrid exists. Only the resonance hybrid exists. So let's state that again. Resonance structures have no physical reality. Only the resonance hybrid exists. Okay. The last point, number 8, has exceptions, and we're actually going to see some. But usually, resonance structures with charges greater charges greater than plus or minus 1 are normally, okay, normally not written, okay? So usually resonance structures with charges greater than plus or minus 1, like a -2 charge or something, that are not written. But there are exceptions. And we're going to see some when we get doing some examples. Now, resonance is important to many things. I mean, resonance is an excellent tool in chemistry because it helps us to understand reactivity. We've already in acid-base chemistry mentioned that you can increase the acidity by resonance stabilizing anions. We did that for carboxylic acids. But I want to show you that you can also use resonance to figure out a reaction. For example, if we look at the molecule CO2 and we knew nothing about electronegativity, we might say, I don't understand how CO2 can react with hydroxide. But if I drew a minor resonance contributor for CO2, that as I took pi electrons and pushed them out onto the oxygen, so we have a double bond, and I get this. If I do the formal charge now, carbon has a positive charge, oxygen has a negative charge. And this is a minor contributor because it violates our octet rule. Yes, it's not a Lewis structure, but it is an acceptable resonance contributor, minor one. The major one's over here, but it's a minor one because carbon only has 6 electrons. But this minor structure allows me to imagine what hydroxide could do to this structure, because hydroxide's negatively charged. He's got lots of lone pairs. And I could imagine he would attack the positive charge. And if he did, I would get this guy. And this molecule, with a minus here, is the molecule bicarbonate, from which we get the molecule we started with, CO3, 2 minus. Okay. What we want to do now is look at some examples of structures, and you'll notice I'm using arrows to move electrons. So I think it would be worthwhile if we took some time to talk about how arrows can be used to show where electrons go. And then we use arrows to create some resonance structures for a variety of organic compounds, and we'll look at some of them. And then we'll close, if we've got time, by revisiting a Lewis structure question that we had earlier in the course. So let's start by considering some rules for the use of arrows for moving electrons. So we're going to make some rules for moving electrons. Okay, and I'm doing this off the top of my head just based on what I do, so there may be exceptions to these rules that crop up, but they will be of general use to give you an idea of how you can use them. One, full-headed arrows will be used full-headed arrows. Okay, that's those guys. They'll be used, full-headed arrows will be used to move pairs of electrons. So, for example, if I have a molecule like this, give you something like this, I can take these pi electrons and move them over here with a full-headed arrow. If I do that, that'll put a double bond here, and the double bond will be lost over here. I'm shifting the double bond, and I'll get CH2, double bond CH. Then I lost the double bond on the other side, and the plus ends up over on that side. And you can check where the plus is by doing formal charge. Okay. What I moved was the 2 electrons in the pi bond, and I use a full-headed arrow. Use of arrows, part 2. Half-headed arrows. Half-headed arrows, such as this guy, sometimes called fish hooks, will move single electrons. So let's change, do a very similar resonance structure, but let's go CH2 this time. CH double bond, CH2. But instead of having an empty orbital, I'm going to give him one more electron and put that lone electron right here, a dot. Now, I can move one electron from the pi bond with a fish hook that way. Move this lone electron that way. And those 2 electrons will make a pi bond. That leaves one electron from this bond, and I'll put it out on the carbon here. And so fish hooks are moving individual electrons. Now, our rules for resonance state that if you got an unpaired electron, your final resonance structure better have the same number. And indeed, though, you'll see I took one electron from one bond and one from the radical to make a new pi bond. And that left one lone electron on the CH2. And so I moved the dot, if you like, to the other side, just like the positive appeared on the other side. And the arrows just help me figure out how these electrons move. So we use full-headed arrows to move pairs of electrons, half-headed arrows to move single electrons. Now, when using a full-headed arrow, some simple rules. Typically, you'll notice in the top structure that electrons usually move away from negative charges, or if there's no negative charge, towards positive charges. So, it's a good rule of thumb. There are exceptions to this, but usually I will stay out of trouble if I move away, move my electrons away from negative charges, away from negative charges, and towards positive charges. Okay. So full-headed arrows move pairs of electrons, half-headed arrows move individual electrons. Typically, with full-headed arrows, I move away from negative charges towards positive charges. Now, with half-headed arrows, you'll notice that I seek to pair up lone pairs of electrons and make bonds, and that generates a new unpaired electron. And I can watch for that. To use arrows properly takes practice, and you'll find it gets easier as you do more and more of resonance structures. So I'm going to draw different resonance structures, and we'll look at them all. And then we'll finish up with benzene. So let's try a few examples. You might get a question which says, for the following molecule, draw 2 more resonance structures. And often you might get something that looks like, okay, you might have something here and something here. And then you might have a positive charge here. And what I could see is immediately, I know I can only move pi electrons, and I see a positive charge, and one might say, okay, I'm going to take these 2 pi electrons and just have them shift over next door. Now, we can't jump. This guy has, by line formula, I know has a CH2. But I know to be a carbocation, carbon, if it has 2 bonds, right, and an H, to get a formal charge of positive, 4 valence electrons, 1 electron, 2 electron, 3 electrons. 4 minus 3, to be positive, must have only 1 hydrogen. I know this. So I know there's only 1 hydrogen there. So towards the positive charge, there's room for the pi electrons. Let me show you the hydrogens in this guy, so you can see why we don't move electrons, say, to this carbon. This carbon has 4 bonds. There's no room. But in my line formulas, I know, if I know my line formulas, that this is the structure. Put a bond out here of this guy. And so carbocations are short 2 electrons, and so I can move the 2 electrons there. And my structure, the pi bond will shift over here. This pi bond's still here, and I get a plus. Why does the plus move over here? Well, if this pi bond shifts to here, you're still getting the bonding electron to this carbon. But this carbon right here, that guy, he's losing an electron, and he becomes positive. Now I can move 2 electrons towards that positive charge here. And so moving electrons can really help you draw the resonance structures. And again, when I move the 2 electrons here, this carbon right there, he loses his bonding electron, he's stored an electron, so he becomes positive. I admit with line formulas and polygon formulas, it is more difficult to actually see. It's a little easier if hydrogens are given on the structures themselves. Let's consider a molecule that is often talked about in high school. And so I'm going to give you the resonance explanation for benzene. The resonance explanation for benzene. Now, benzene has hydrogens on it. It can be drawn like this. Or I can give you the line formula. And I know from a polygon formula, if I count bonds, each carbon has 3 carbon bonds, so there must be only 1 hydrogen off of it. In high school, you may have seen benzene drawn like this. Well, it turns out that benzene, when drawn with a circle in it, is being represented as its resonance hybrid. Now, the resonance hybrid, that little circle, is saying that pi bond, those double bonds, are shared amongst all the carbons. In other words, those pi bonds are, if you like, delocalized over all the carbons. That's what the circle means. And that violates valence bond theory. Valence bond theory says bonds can only exist between 2 atoms. You can't take bonds and smear it out over many atoms. To handle this concept, valence bond theory introduces resonance. And I can draw the other resonance structure for benzene by assuming the electrons, the pi electrons, all shift 1 bond in the same direction. If I do that, I get another resonance contributor who's identical, so he makes equal contribution. Right? Now I couldn't just move 1 to a pi bond. But you might be saying, well, can you move and reduce charge separation? Could you, for example, well, let's actually put it down here. Well, let's do it on this one. Instead of just shifting the bonds again and getting the exact same thing, could you take the bi bonds and make a lone pair here? Rather than shifting to another pi bond, could you leave those 2 pi bonds here and take the pi and make them a lone pair here? Well, if I do that, remember each carbon has 1 hydrogen. There's a hydrogen here with 2 carbon-carbon bonds. 1, 2, there's a hydrogen 3. 4 minus 3, that's a positive charge. Why is it positive? I took a pi electron away from this carbon. And this guy has a hydrogen, so he has 1, 2, 3, 4, 5. 4 minus 5 is minus 1. We've created a structure with charge separation here. And I could draw a lot of structures where I do this, but as soon as you get charge separation, as soon as you get a structure that only has 6 electrons around it, this carbon has 6, this one has 6 electrons around it. These are very minor contributors. So often when we draw the resonance structure of benzene, we only, and I'll take this one arrows away if I can, draw it again. Why not? Okay, I can do that. Alrighty. So let's just draw it again. So These two resonance structures that I've drawn here are major contributors, and you often don't draw the minor contributors. Now, in terms of resonance explanation for benzene, we know the resonance hybrid is more stable than the resonance structures by what is called the resonance energy. This resonance energy, this difference in energy between a resonance structure and the resonance hybrid, in this case, is 36 kilocalories per mole. Now, that raises a whole nother issue. How on earth do you measure an energy between a molecule that exists and one that doesn't? And we'll leave that for another time. So when you draw benzene with a circle in it, you're actually representing the resonance hybrid, but it's not a legitimate Lewis structure. When you draw benzene with double bonds in it, well, you're drawing a hypothetical structure. But double bonds in benzene are not isolated between two atoms, fixed. They can shift, and we represent this by drawing resonance structures. But if we pick one resonance structure, the resonance hybrid is 36 kilocalories per mole more stable. Okay, I want to revisit some homework that we did, and that was the three structures for SCN minus. If you remember the homework for SCN minus, we said there were three Lewis structures you could draw, and all of them were acceptable solutions. Well, the answer as to why you can have three structures for SCN minus now is that they are all resonance contributors to the resonance hybrid. All right? So what we should do now is draw these three resonance contributors, and I'm going to do that. And if you remember correctly, we'll start with 1, and you could derive 1 from its Lewis structure. Okay. But I'm going to use arrows to generate the others. Okay, so I'm going to use arrows, and I'll use a different color for the arrows. I like red. We'll use red. How do we go? This was one of the Lewis structures, if you remember, that we generated. You can check it out in the homework solution section of this Scribblecast. And what you have in that solution, that you could generate this and also generate 3 more. But what I want to show you is that if you had generated one structure using your Lewis structure rules, using arrows, you could get the others. I'm going to take a lone pair, and in fact, what we should do is maybe calculate first the formal charge. So I'll go back to blue. And if you remember, if you look back at your homework, the formal charge of nitrogen, remember nitrogen has 5 valence electrons, 2, 4, 6, 1 for the bond, 7. 5 minus 7 is minus 2. Carbon, 4 minus 1, 2, 3, 4 is 0. 4 minus 4 is 0. And sulfur had 6 valence electrons. 6 minus 2, 3, 4, 5. 6 minus 5 is plus 1. So this structure had this formal charge. Now remember my rules said typically we're going to move electrons away from the minus charge towards the positive. So I'm going to bring this lone pair out, and I'm going to make a pi bond. Now, if I do that, though, if this becomes a double bond, I got 2, 4, 6, 8, 10. That's too many electrons. So I'm going to shift a pi bond and make a lone pair out on sulfur. If I do that, I get this structure, which was one of the other Lewis structures. And I can do the formal charge for this structure. Sulfur has 6 valence electrons from a periodic table. 2 lone pairs, that's 2, 4, 5, 6. 6 minus 6 is 0. Carbon has 4 valence electrons from a periodic table. Count up the electrons and bond. Remember, in formal charge, you only use half the bonding electrons. 1, 2, 3, 4. 4 minus 4 is 0. And nitrogen has 5 valence electrons. 2, 4, 5, 6. 5 minus 6 is minus 1. Now we can draw the last resonance structure, and again we're going to get it. I'll use red for the arrows. How do we get it? Well, I'm going to move away from the negative charge, so I'm going to bring a lone pair in and make a triple bond. Again, that would put too many electrons around carbon, so I'm going to move away, a lone pair away from the sulfur, and that will give me these two. Sulfur, 3 lone pairs now in a single bond, and then nitrogen will have a triple bond and only 1 lone pair. And now when I do the formal charge calculation, sulfur, which has 6 valence electrons, 2, 4, 6 plus 1 is 7. 6 minus 7 is minus 1. Carbon has 4 electrons from the periodic table, 4 from the bonds. 4 minus 4 is 0. Nitrogen has 5 valence electrons from the periodic table, 1 lone pair, that's 2, 3, 4, 5. 5 minus 5 is 0. And I've generated, by using arrows, all 3 resonance structures. And what's great about this structure is the solution to these 3 structures, solution to the Lewis structure question. And resonance really explains why you had 3 solutions. None of these structures exist, just the resonance hybrid. Now one could ask the question, which of these structures is the resonance hybrid most like? We can apply all our rules. We could start with rule number 4. Rule number 4 states that structures that have filled octets around each atom, but period 2, makes greater contribution than structures that don't. But what's interesting, if we count 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, you do that around every atom, they all have filled octets. So rule 4 doesn't help us. Rule 5a, if I review Rule 5a, it says more important structures have less charge separation. So let's label these structures A, B, and C. Well, I can now begin an explanation because I see our first violation. In structure A, we have more charge separation than structure B or C. So because of this, 5A is violated. That suggests structure A is a minor contributor. And so I'll make note of that. We will also note that 2 other areas, or 1 other area is violated, and that is the rule that you normally don't draw structures with more than plus or minus 1. And so it's a minor rule. The main reason is charge separation, but a minor point would be nitrogen also has a negative 2 charge. That's a lot of charge on the nitrogen atom. So, but if we compare B and C, they're the same in charge separation, so there's no help. We have to go to 5b, which states the more important structure is a structure that puts a negative charge on the electronegative atom. And so we have to look at 2 atoms here. And hopefully I memorize my electronegativity trend. And I take a close look, and I see nitrogen has a negative charge in B, and C, sulfur. Who's more electronegative, nitrogen or sulfur? Well, if I memorize my electronegativity trend, I know that nitrogen's more electronegative. So B structure is the major contributor. So if I was to rank this, I would say B makes a greater than contribution than C, who is greater than A. In this structure, the resonance hybrid is most like structure B. Now, if I was told to do this on a test, I would have to be willing to show my work. And I'd do a Lewis structure for one of the structures, total number of valence electrons. I would show how I generated the structure. And then the other 2 structures I would get from the original structure by moving electrons, as you see here. I would also, if it said explain and justify your answer, I would have to write out the following. And I'm not going to take the time to write it all out, but I'd simply have to say structure, all these resonance structures have filled octets. Structure B is the greatest contributor. Structures B and C are greater contributors than structure A because they have less charge separation. Structure B makes a greater contribution to resonance hybrid because it places the negative charge on the more electronegative atom, which in this case is nitrogen. Right? Structure C is a greater contributor than A because structure C has less charge separation. Structure A is the minor contributor because it has the greatest charge separation and it has a -2 charge on nitrogen, which is less favorable. Adding all these comments together, I explain my ranking. So watch the questions you're given on a test and make sure if it asks for a justification, you explain your B greater than C greater than A ranking. Okay, in detail. Well, there you have it. That's a quick introduction to resonance and resonance theory.